Okay, I'm just going to show you how to do the first sample problem on the free body diagram homework, okay? So the directions are basically here, okay? And there's an example. So we have a bicycle pedaling down a hill. Friction is negligible. So I know you draw free body diagrams free from its surroundings, but I usually do draw the hill. So here is the bicycle, okay? And we're going to go ahead and label the forces that are acting on this bicycle. So let's start with this, okay? So let's see. Is there a weight force? Yes, there is. It acts straight down, and I'm going to draw it nice and big so I can separate it into its components. And we call that F sub G. All right. Next, is the surface supporting it? Yes. So we're going to draw a normal force perpendicular to the surface. So here comes the normal force perpendicular to the surface. Okay. F sub normal. All right. Is there an applied force? Well, the bike is pedaling downhill. I would call that an applied force going downhill. FAPP. All right, next question. Are there any strings involved? Nope. All right. And then friction. And friction is going to be parallel to the surfaces in contact opposite motion. So since it's going down the hill, all right, the velocity is going this way. We don't draw velocity vectors on free body diagrams, but you can draw kind of to the side. Since the velocity is going down, the friction is going to be going up parallel to the surface. And that's it. Now we're done with our free body diagram. Now at this point, we need to separate the weight because into its perpendicular and parallel components. And again, because everything interesting happens either parallel to the plane or perpendicular to the plane, we're going to separate the weight into a perpendicular component and a parallel component. Okay, it doesn't really matter whether you draw the parallel component here or here, as long as it's going this way, right? Okay. And notice that these make the legs of a triangle, they're perpendicular, and that the hypotenuse is the weight force. All right. Also notice that whatever this angle is always going to be the same as this angle here. All right, now, so we've drawn the free body diagram. We did it kind of to scale, all right? And we separated the weight force into its parallel and perpendicular components, and then realize this isn't here anymore. It's now been separated into these guys. Now, why do we draw this? The whole point of drawing free body diagrams is to write specific forms of F net equals ma, Newton's second law. And we're going to do this for two directions. We're going to do it for the parallel direction and the perpendicular direction. So looking at my picture here, in the parallel direction, I have three forces. I have a friction force, applied force, and also the parallel component of the weight force. Some of these will expect to be negative, but there. And these all add up to ma parallel. We don't know whether this is accelerating in the parallel direction, so we're going to leave this alone. In the perpendicular direction, I have two forces, force normal and force perpendicular. And it never accelerates in the perpendicular direction on inclined planes. That's just not how they work. So surprise, surprise, the normal and the perpendicular are going to be balanced as they always are in this class. All right, at this point, we are done. We have drawn the free body diagrams and we've written specific forms of F net equals ma. Have fun.